Hey guys, welcome back to Genius Learning. Alright, I want to take a look at another quantum mechanics problem. And here we have something similar, but consider a particle with a Hamiltonian represented here. And the question is, if the energy of the particle is measured, what are their possible energy values? So we have a Hamiltonian, right, the energy of the particle, and if the energy of the particle is measured, right, with this Hamiltonian, what are the possible energy values? Okay, so energy values, right, immediately we should think we need the eigenvalue equation or characteristic equation, which I'm not sure why they call it that, but we need eigenvalues, okay? And so to get eigenvalues, we use the determinant. Inside the determinant, we have the Hamiltonian minus lambda and an identity matrix equal to 0. Okay, so this equation here is how we find our eigenvalues. All right, so let's start, let's plug it in. We have the Hamiltonian inside of our determinant, right, given to us here. So I'm going to distribute that E naught in, and we're going to get 4 E naught. From the first term, we're going to get 3I E naught from the second, negative 3I E naught down here, and over there we're going to get 4 E naught in the bottom right. Okay, so we have minus lambda, and then we have the identity matrix, which is 1, 0, 0, 1. And all of that is in the determinant, okay, equal to 0. All right, our next step, let's distribute this into this matrix and then subtract this, or subtract it from this side. So we have our determinant is now going to have 4E, this one here minus lambda, top left, right? This one here is going to be just 3I E naught because this is 0. Okay, we have this bottom one minus 0, so we're just going to have 3I E0, and then here we have 4 E naught minus lambda, so 4 E naught minus lambda, and that's our new determinant. Okay, now let's evaluate. We got this times this minus this times this. Okay, so this times this is going to be, we have 4 E naught minus lambda, which is this one times this, right? 4 E naught minus lambda. And then minus, okay, we have minus, let's just write it out loud. I'm going to put minus this times this. Okay, so we have this negative, and this negative is going to make a positive. Okay, and we have 3I E naught times 3I E naught. All right, and all that equals 0. So I times I, we know, is negative 1. And so this side here is going to be negative 9 E naught squared equals 0. I'm going to bring this down. 4 E naught minus lambda, 4 E naught minus lambda. Okay, and let's see, everything looks good. Okay, so now let's FOIL this out and evaluate. We have 16 E naught squared. This and this, we have minus 4 E naught lambda minus 4 E naught lambda plus lambda squared, so that's all of this, and then minus 9 E naught squared 0. Okay, so each of these is separate. All right, so now let's combine things. What do we see? We got lambda squared alone, so let's put lambda squared, and then we have this is negative 8 E naught lambda, and 16 minus 9, 7 E naught squared equal to 0. Okay, so we have this, and we don't need quadratic because I think I can factor, and we can have lambda negative 7 E naught and a negative E naught. So that'll give me positive 7, and both of these combined. Yeah, perfect. Okay, so now I solve this and I solve that one. I'll label this one 1, which is E naught, so that's this one over here. And then this one over here, I'll label lambda 2. Just because you could have labeled the other one, it doesn't really matter. Okay, so now these are the energy eigenvalues. So the energy eigenvalues. These are the energy eigenvalues that correspond with this Hamiltonian. Okay, and now let's move this slightly. Okay, so now let's move over here. Okay, and our next question is, let's see, we got B. Okay, what are the possible states that the particle can be in after the energy of the system is measured? Okay, so what are the possible states that the particle can be in, right? So the possible states that the particle can be in after the energy of the system is measured. So we measured the energy of the system, right? And we found that these are the eigenvalues. These are the possible energy values that it can have. And now we want to know, what are the possible states that it can be in? Okay, and so for that, we're going to need an equation. And that equation is how we find the eigenvectors. So we have H, and we have some eigenvector, right? And then we have lambda n, and then the same eigenvector. So this is how we find eigenvectors, or eigenvector equation right here. Okay, we have the Hamiltonian, and then we have these two states, right? These two vectors, state vectors that are the same, and our lambda. So this is also subscript n, all of these. Okay, so now let's get to work. First, we have two energies, right? And so what are the possible states it can be in? Well, let's first look at the energy eigenvalue, this one, number 1. We'll call it number 1. So we're gonna do two solutions to see what states it can be in, with this energy and another one with this energy. So for lambda 1 equal to E naught, all right, we're gonna go with this one first. Let's see what happens. Okay, so first we need to assume, okay, let's go over here. We need to assume that the eigenvector, right, eigenvector, like the representation is just 1, and that's B. Okay, A B, and eigenvector is denoted as 1, the state. Okay, so we need to use that first. All right, and now using this equation here, we can solve. So let's do the Hamiltonian, right? So we have E naught, 4, 3i, negative 3i, and 4, right? Then we have the state that we assumed, right? The eigenvector we assumed that that we're looking at. Okay, so a b equals the lambda that we chose is E naught. Okay, and again, the state vector is that. All right, so let's do the top first. All right, so let me get a smaller marker here. What color? All right, so let's go with this. All right, so let's do the top first, and by top I mean you should know this from linear algebra, but we're gonna deal with the top first, and so we have E naught, okay, which is gonna cancel out, but we got this times this, which is 4a, plus this times this, so plus 3ib equals E naught a. So that's what I mean by the top. So we're gonna go this times this plus this times this, right? And this one times that. So that's the top part. And now the bottom is gonna be, let's write the E naught on the outside. We're gonna have this times this, so negative 3ia plus this times this. So plus 4b is equal to E naught times b. Okay, so you can clearly see that the E naught cancel. And let's work with the top one. We have here, let's see, we have this top equation here. Let's move it this way, right? And solve. Let me get a darker color here. Okay, so we're gonna have 4a, and if we move this a to this left side, we have a negative a, and if we move this 3ib to the other side, we have negative 3ib. Okay, let's further solve here. We have 3a equals negative 3ib. The 3's cancel, and we have a is equal to negative ib. Okay, so let's hold that for a second. All right, and let's use normalizing the normalization equation. Okay, so let's see. Normalization equation, we will be using, all right, the normalization equation here, a determinant square, we got b equal to 1. Okay, so it's important that we normalize this value that we just got to fit within our parameters. Okay, so using this will do that for us. Let's plug in a into here and see what we get. Okay, we're gonna get a is equal to negative ib squared plus b squared equal to 1. All right, and I like to do these separate because they confuse me sometimes, so I'm just gonna write it on the side over here. Negative times a negative, right, is gonna be a positive, but I times I is a negative. Inside of this absolute values, that ain't happening. So we have 2b squared equal to 1. Okay, so everything that comes out of these two absolute values is going to be positive. All right, so we have this for b, and finally we have b is equal to 1 over square root of 2, which is our true value. And with that, now we can plug this into here, right? And we have, let's see, we have a equal to negative I, and where b is at, let's put in 1 over square root of 2. And so a is going to equal, or let's write it over here, a is going to equal negative I over square root of 2. Okay, so now we found our a and b, and let's write our state vector. Let me move this up a little bit. Okay, I'll put it over here. And so let's write it in red. So we assumed initially our eigenvector was 1, right? Denoted as 1, and a and b for the constants we didn't know. Now we found those constants, right? And so let's replace the constants in here and rewrite our eigenvector. Our eigenvector is now going to be 1, the energy state, and then 1 over square root of 2, negative I, and 1. Okay, so this is our eigenvector. So a is negative I over square root of 2, which would go up here, and b is 1 over square root of 2, which would go down here. From both of those, you can take out a 1 over square root of 2, and on top you'd be left with just the negative I. On the bottom you'd be left with just 1. So this is our eigenvector for this energy eigenvalue. Okay, and now let's look for the second one. And again, I ran out of paper. Okay, sorry about that. So all right, so now we found the eigenvector for this energy eigenvalue. Now let's look for the second one. And so the second one is here, right? So now for lambda 2 equals 7 E naught, right? Let's see what we got. So just like before, all right, let's assume, right, the eigenvector can be represented as state 2 with, we're gonna change up the constant or the variables just to not confuse, put C and D this time. But just know that you can use A and B every single time. I just want to distinguish, this is A and B, and then now we're searching for this energy eigenvalue, and we're going to use C and D. So just a distinction, doesn't really matter. All right, we're going to need our eigenvector equation, and that's Hamiltonian. We got these states, subscript with n, right? Okay, and now let's plug it in. So again, we're gonna put our Hamiltonian. We got E naught, we got 4, 3i, negative 3i, 4. We got CD this time. Instead of AB, we got CD, and then equals the eigenvalue is going to be, what did we say? We get 7E naught. And then again, our state is C and D, right? Okay, so same as before. Right, let's do the top. okay? And this time we could just cancel out the E naught from the beginning. We don't need to really write it all out like we did last time. I just wanted to show more of the process, but this times this, 4C, plus this times this, 3ID, is equal to 7C. All right, and then the bottom is going to be negative 3I times C, and then 4 times D, plus 4 times D, equals 7D. Okay, so these are the two. Let's work with the top one here. And again, you can choose either one. You can choose to solve for D first or C, or use this bottom one. It really doesn't matter, just preference. So let's work with the top one here, and let's put the 7C on this side, 3ID on the other side, and we have 4C minus 7C equals negative 3ID. Further solving, we see that we get negative 3C equal to negative 3ID, and then these cancel, the negatives cancel, we get C is equal to ID, okay? We can't do anything with this yet. We need to plug it into our normalization condition, and so let's do that. And we got here C squared plus D squared equals 1. Absolute value of both of those. All right, and let's see. Let's plug in this C in here. We get ID squared plus D squared equals 1. Okay, and then you can see that I times I, we're gonna have D, 2D, right? We're just gonna put 2D squared, just like the other one. I wanted to say more, but really it's the same process. So here we're gonna get D is equal to 1 over square root of 2. And so this is the true value now that we normalized it. And plugging this into here, right, is gonna give us C is equal to I, and then the value we got for D is 1 over square root of 2. And I'll write it here right next to it. C is equal to I over square root of 2. Okay, so now we have our constants, right? These are the values. And since we assumed in the first part that our eigenvector was state 2, right, equals C over D. C is going to go up here, D is going to go down here. We're going to take out square root of 2, 1 over square root of 2. So we have 1 over square root of 2. And then finally we have I and 1. Okay, so this is our eigenvector. Okay, and now we have one final question. Okay, so let me see if we could do a recap here. We got the energy of the particle measured. If the energy of the particle is measured, what are the possible eigenvalues? So we have the energy of the particle, right, given to us by our Hamiltonian. Now we put the eigenvalue equation to work, plug it in, solve, and we get these two values for the eigenvalues and the energy eigenvalues, right? Now it's asking us, what are the possible states that the particle can be in after the energy of the system is measured? So after we've measured the energy of the system, what are the possible states it can be in? And so checking our first eigenvalue for the energy, we use our eigenvector equation, right? We assume that the eigenvector is denoted by, 1, the state vector, and the constants we need to find. Okay, we use the equation, the bottom of the matrix, I solved for the top specifically. You can solve for either one and get a value for A, use the normalization condition. You need to definitely use this. Plugging that in here, we find the value of B. Plugging B into what we got earlier, we get the value of A. So now we have the constants. We plug it into what we assumed earlier could be our eigenvector. So now our state vector 1 is denoted here, and we did the same process for the second energy eigenvalue that we found. Okay, it's roughly the same process. We found the eigenvector, right? And so in another video, I'm going to show the last part of this problem, which shows the system being prepared in an initial state, and we want to find the time evolved state at some later time in matrix form. Okay, so we'll do that in another video, and I hope this was helpful for you guys. All right, thank you for watching.